nice roll. And then chapter 8, we'll talk about the canonical divisor of a toric variety, and in particular talk about the nice case where that divisor is a Cartier divisor, and that's going to lead to the notion of a reflexive polytope. So that's sort of the plan for today. So a polyhedron is an intersection of finitely many half spaces. So a polyhedron is basically can be written as a Minkowski sum, where this is an actual polytope. So there's our sort of bounded part. And then this is the part that goes off to infinity, and this is simply a polyhedral cone. And it's called sometimes the recession cone. So basically this is sort of tells you how it goes off to infinity. And it turns out we actually have a formula. So when we have this for P is above, and I mean for this P, turns out that the UIs tell us what's going on. Maybe you simply take all the AIs and just set them equal to 0. You know, this is an actual half space through the origin. When they intersect finite many of these, I actually get a polyhedral cone, and this is sort of, the half space representation of it. But what's interesting, so when you have a polyhedron, P might not have vertices. Let me draw two pictures, one with vertices and one without. So here I imagine that we're in the plane. Okay. Thank you. So there's a nice just polyhedron in the plane, and it turns out that in this case, one way to think about the recession cone is that if you get really far away from the polyhedron, polytope stuff just looks smaller and smaller, and what you just see is the cone. And so the recession cone is this stuff. So that's the cone. And then in this case, see there I actually have some vertices, And for example, you can actually pick that guy to be Q. In this case, there's a nice minimal choice. Although I should point out that, this particular one, gives you permission to, be sort of dumb. Because for example, I could also pick, that polytope Q, give the same thing. And so that's one of the things that you play with in some of the exercises, is that when you play with Q, it'll have vertices. Some of its vertices might contribute to vertices of the polyhedron. Some of its vertices might not. So that's something. And so the distance between vertices of Q and vertices of P is sort of, that's how you pick a most efficient one. But the problem is, as I said, you might not have vertices. So now let's take this picture lying in the plane and make it three-dimensional. So now I'm going to sort of imagine, so this is a little hard to imagine what's going on, is, so take this guy and just put it flat and then extend it off to infinity in all directions. So these two vertices become these two lines. And again, so there's a facet here, and a facet I sort of can't see that comes from this one right here. And so in this case, there's the our friend the polyhedron. Notice now there are no vertices. In fact, the minimal faces are these two lines. But again, if you go really far away and look at this, then what you see for the recession cone is basically just this facet and that facet. It's like, when these two things come together there, the same thing happens. So this is a little hard to see, but this is a drawing of a quarter space. Here it's a quadrant, and then when you cross the real numbers, it becomes a quarter space. And there are various choices. So there are lots of choices for Q, because in this case I could sort of pick a nice minimal choice. So even though there were lots of choices, I actually had a minimal choice. Here I don't really have that luxury. For example, here's one choice of Q. I could pick those two guys. But you can see I could, I could do that. So basically, there's lots of choices for Q. So in this kind of situation, even though that's uniquely determined, there's a lot of leeway here. And notice that the one difference between these two cases is that the recession cone is strongly convex, and here it's not. Because notice that this cone contains an entire subspace. And so it turns out that one of the first lemmas is let V be the set of vertices of P. So the first thing that you prove is, actually V might be empty. So, like I say, this, for this polyhedron, V is definitely empty. And it turns out that being non-empty is if and only if my cone is strongly convex. And part of the idea is that, when I form, Q plus C to get P, I take sort of this minimal face here, and it basically is added to every vertex of Q, and that's sort of how I get the minimal faces of the polyhedron. And then it turns out in this case, when this is non-empty, then in this particular case, we do sort of get a minimal choice for what Q is. It's exactly here. Namely, we get that P is the convex hull of the vertices plus C. So in the case of the recession cone is strongly convex, then we sort of have, we do there have a canonical choice for the Q part. Now I'm going to talk about lattice polyhedra. Now for lattice polytopes, it was easy. You took the convex hull of a bunch of lattice points. And so for a lattice polytope, sort of the way you tell it's a lattice polytope is that the vertices are lattice points. Well, mild embarrassment, I don't have any vertices. And so the answer is we're just going to punt. And so it turns out that I'm not going to talk, you can give a general definition of lattice polyhedra. You basically say that every minimal face has a lattice point. And what we're going to do is focus on a special case. And the special case we're going to focus on, not surprisingly, is when we actually do have vertices. So this is the definition in the book. And there's basically two things going on, because what's the data in the strong, and so like I say, I'm going to have this be strongly convex, and so, but of course I also, if I want it to be the lattice, I want it to be strongly convex rational polyhedral cone. Like I say, the fact that I'm saying strongly convex, that's what's doing it in the special case. But then, of course, once I'm in the strongly convex case, I have vertices, and then the vertices in C then determine P. So the next obvious thing to want is that vertices of P lie in M. And of course, this case right here, where I think of this as E1 and E2, that's clearly, because and notice that this is strongly convex and rational. My vertices are rational, so that's an example of a lattice polyhedron. And then what we do is pretty similar to the polytope case. We want to focus on full dimensional ones. And in that case, we actually have a pretty standard way to do it. We basically have a facet presentation. So, it looks exactly like what we have for polytopes. And again, this is, a lattice polyhedron. Turns out I keep wanting to abbreviate polyhedron to poly, but the problem is polytope has the same abbreviation, so I actually have to write it out. But that's good, it slows me down. And although I do reserve the right to spell things badly.
That's actually correct, I like it.
And so notice we get the exact same kind of thing we see for lattice polytopes. because now that's going to be an integer. This is going to be the first, for each facet, this is the first lattice vector in the normal direction. So all that fits together pretty nicely. Then also we can take a polyhedron and make a cone out of it. And that's useful for various constructions. So basically it's going to live in one higher dimension, and I'm going to sort of put copies of P at different levels, and the level is going to tell me how to scale it. So it's going to be m lambda in mr cross r. I want the lambda to be greater than or equal to 0. And I'm going to be now making this assumption all the way along. So it's going to be basically this guy scaled by lambda. And what the picture looks like is, so this is going to be pretty challenging. So imagine I'm in three-dimensional space, and so here's the origin. So here's, say, height 1. And so I'm going to be taking this guy, and I'm sticking it here. But then what's happening is, what this is doing is sort of rescaling it. In fact, when I have P equals Q plus C, so that's at height 1. At height lambda, positive lambda, I basically get, I'm rescaling that, so I'm basically making the polytope bigger or smaller. But what's the positive, what happens when I rescale a cone by a positive number? What do I get? I just get the cone. So the point is that the rescaling has no effect on the cone. So like I say, so in fact what would look like is that you get these lines going up, and so up here I get a bigger, so this would be Q, this would be lambda Q. So it sort of look the same, except that it's like in this case it's like I'm chopping off larger and larger corners as lambda gets bigger. And then of course at height lambda equals 0, what survives? Just the recession cone. So what I get down here is just C. So it's a very pretty picture that you get that. And like I say, that's going to come in when I take lattice points of this, then I'm going to get some interesting stuff. And then I'm going to talk about the toric variety. And now we get really evil thing, because that used to mean one thing. Now it means something different. What does it now mean? Full dimensional lattice polyhedron. Yeah, so context is important. So two constructions. One is high-powered and one is more down to earth. I'll start with the more down to earth one. And the more down to earth one is that P has a normal fan. Just as in chapter 2. And this is part of why I want our one to have vertices. Because remember when I took a polytope, the polytope had a normal fan, and remember the smallest faces, the vertices, gave us the biggest cones in the normal fan. And because I'm making this assumption about my polyhedron, I still have vertices, so I can play the exact same game. In fact, it reuses the same notation. A vertex V gives, we sometimes called it CV. So that's the cone. So in a sense, that's sitting at the vertex of a polyhedron and just looking out and seeing what cone do I see. So that's taking place in MR. And then I get sigma V, and again, V is the vertex. And so that's the dual cone. So this is really evil. That's a V and that's a dual. So make sure they look different in your notes. That's the thing about LaTeX. In LaTeX, they actually do look different. And so the theorem is that the normal fan, which consists of these guys and their faces, is a fan in NR. But now something interesting happens. That what's the support of this fan? Let me do an example. So this is example 7.1.7. So I'll do the example and then I'll come and fill in what's going on here. So let's take the cone we've been playing with, the one we've been playing with. Well, notice that I have three normal vectors. I have this guy, that guy, and that guy. And so, right there, so, that vertex gives me a cone, and it gives me a cone. So that vertex gives that cone. This vertex, they're the two normal vectors. It's that one and that one. So here's sigma p. And just out of curiosity, that's the cone of what? We've seen it before. And this is the blow up of what? Blow up of C2 at the origin. So see, now we have a new way of getting some interesting varieties. It used to be we take a polytope, take the normal fan, get an interesting variety. Now we can take a polyhedron and get something interesting. But notice that the support of this, it's not a complete fan. So because again, in the polytope case, the complete fan is, it's a complete fan. And here what it is remember that we have, remember that P is equal to Q plus C, the recession cone, and turned out what you can prove is that support is the recession cone. And notice that here I'm assuming that this is strongly convex. And this is in NR. When I look at the cone in MR, if I have a strongly convex cone, what do we know about the dual? What property does it have? It's full dimensional. So that's another reason why I want to make this hypothesis right here in order to get a strongly convex. That strongly convex means I have something full dimensional. Let's just actually do a reality check. Suppose I have a polytope, an actual polytope. Well, that's a polyhedron. But my polytope, it has this decomposition. So what's the recession cone of a polytope? It's the zero cone. What's the dual of the zero cone? The whole thing. That's why the normal fan of a polytope is complete. So it all fits together very nicely. So this is pretty stuff. So this is so remember I get this and then the definition is that the toric variety of the polyhedron is just the toric variety of the normal thing. So that's the very down-to-earth way of doing it. But it turns out that modern algebraic geometry has, some very powerful ways of creating varieties. And so remember, I'm doing two constructions. So P gives a normal fan, gives this. But P also gives a semigroup algebra because I have this very nice cone here. So it's C of P, then I just take the lattice points in it. But this is not any old semigroup algebra. This is graded by the last coordinate, namely that one right there. So I have generators at height 0. That corresponds to the lattice points in the recession cone. I have stuff at height 1, that just is lattice points in the polyhedron. At height 2, it's lattice points in the twice it, and so on. And so what I get is a graded ring, and then any graded ring well, it's like, if I have just a ring, I have this gadget called spec that produces an affine variety. But a graded ring has something called proj. So a graded ring, if I just have a graded ring R, then we get proj of R. And the point is that proj of R, so this is described in section 7.0, and it turns out that there's the stuff in degree 0, and this is a classic example. This is a projective morphism. Now, it turns out the one example that you're familiar with is when R is just this ring where the degree of xi is equal to 1. So I look at the usual polynomial ring, but now I think of it as a graded ring where all the variables have degree 1. So in this case, what's R sub 0? It's just, just the constants. And in this case, we have this map. So in this case, we're just mapping to spec C. We have this projective morphism. And of course, this is just projective n space. And so what we're doing is sort of this very, a graded ring. This graded ring gives Pn. This graded ring gives this more sophisticated thing. And then the theorem is that XP is proj of the semigroup algebra you get from this. And so it's C of this guy, again regarded as a graded ring. So this is really where we touch base with some of the more sophisticated stuff. Now what I want to do is I actually want to work out, because remember, see in this case, I got just, the usual fact that, I get this projective morphism just mapping Pn to a point. Any proj gives this guy. Well, so that means this guy is going to come with a projective morphism, but it's going to be based on sort of all the stuff there. So how do you say that carefully? So let's write this down. And so in this case, for R being our graded stuff, the stuff at degree 0, and again that's just this, and so that's just the semigroup algebra of C intersect M. And so let's, and so that means that we get XP, and so, again, going from proj R to spec of R naught, yeah, so we get, so again, the general theory tells us that this is XP. This is clearly going to be an affine toric variety. And so the question is, what affine toric variety? And the answer is, remember, there's lots of ways to describe an affine toric variety. One is, it comes from a semigroup algebra, so we've already got that description. But the idea is I want to put it in the context of the cones, because that's the world we're living in right now. And so it turns out that there's a cone involved, but we have to be a little careful. Because it turns out this picture is a little deceptively simple. Because in this case, the recession cone is C and its dual are just the first quadrant. So we have to do something a little more clever. Because remember that if I want this to come from a cone, I need the dual of the cone intersect M. So and when we dualize, we realize it's not quite there's one detail we have to worry about. So remember that we've got our recession cone, which is strongly convex. So basically, my first guess is that should be what sigma is. But this guy is full dimensional. But it may fail to be, this guy may fail to be strongly convex. We want our cones in NR to be strongly convex. For example, I could imagine here's an interesting polyhedron. And so that's P. What's the recession cone of this guy? And the answer is just this ray. That's strongly convex. That's perfectly good. We like strongly convex recession cones. But notice that what's the dual of this? It turns out just to be a half space. So it's not strongly convex. So I can't quite just say, just take the sigma to be the dual of this. You have to be a little more clever. And so, of course, what we get is we know how to. This is the largest subspace. And of course, in this case, that would just be the y-axis. Because when I take this and intersect with its negative, they meet there on the y-axis. So how am I going to turn my dual cone C check into something that's strictly convex? What am I going to do? I'm a quotient. Yeah, so that's exactly right. And then so what I do is I'm going to call this n sub p because it depends on p, and it's going to be n. Because remember, I want a lattice, so I just take the lattice points in the subspace quotient out. This is saturated, so this is a nice free abelian group. So this is definitely a lattice. And then I'll call it sigma of P. It's basically this guy, mod W in n sub P made into a vector space. And the whole point is this is strongly convex. And of course, in this particular case, when I slurp this so here's W. When I slurp W to a point, and then right here, so that's what I call that's sigma P. So now I get something strongly convex. And so it turns out that what you can prove is that spec of R naught is so let me say it first in semigroup algebra. So when you chase through all the definitions and stuff, you can prove that and so you have to do a little bit of careful work, because of course when I take this, its dual lives in the dual of this, but it turns out that works out well with that, and so you get a natural isomorphism there, and so you get that spec of R naught. And again, that's the gadget. That's the gadget we're trying to figure out right here. It turns out that this really is the affine toric variety of sigma p. And so the theorem that we get, so this is the first result. So at 7.1.10, so it turns out just for being lazy, I'm going to call this just U sub P. So it's just the affine toric variety that I build out of the recession cone of P. So notice my general nonsense over here, the theory of Kraj says that's a projective morphism. But it's more than just being a projective morphism, it's toric. And then furthermore, the fact that I'm projective over something pretty nice that's affine, that turns out to be enough to show that this is quasi-projective. Any questions? And let me make one comment, because turns out that it's pretty easy to see that it's what you chase through definitions, the fact that this guy is toric, because remember that I have the I have these cones right here, but remember this was the dual cone of C. And notice that what we're doing is we're sort of mapping that to sigma p. That's the construction we have right here. And so that means that every cone in here maps to this guy, and that's what makes it a toric morphism. So the fact that it's a toric morphism is, so basically this implies toric. And then also when I look at this map right here, this is what, this is sort of the phi bar r. This is the map on the ends, and the bar means it's the, so this is phi. This is the map on the ends, and that's when I tensor it up over r. And the other thing is that notice that in this construction, I took this cone and I modded out by a subspace to get this. And so that means that, when I basically take the inverse image of this back in here, well, I'm basically adding in the subspace, but that's already in here. So when I take the inverse image, I just get this guy back. And so that says that when I have this guy, I just get that. And of course, that's just the support here. And notice that, so when I have a map from one fan to another fan, here's the support of the source, here's the support of the target. The fact that phi inverse of this support is that support, what does that imply about the map? That implies proper. So this implies that phi is proper. And of course, in one sense, we know that because we know projective implies proper, but this is a way of sort of seeing that, yes, the whole picture is very consistent, that things fit together the way we want. So the last 15 minutes, I want to talk about the general idea. You know, here I've been constructing some very specific projective toric morphisms. So the idea is that I have a toric morphism I want to get the prime in the right place because I'm going to map one toric variety to another. So it's X sigma prime projective. So just need to remember the setup for a toric morphism, which I reviewed a little bit. That, you know, I have phi bar, I'll tensor it up with R. Well, the thing is, projective implies proper. So we clearly, if I want to be projective, I clearly need proper. So we want sort of the more general version of that. We certainly have that. And then let's just remind ourselves a little bit of the stuff that Hal did. Hard to believe it was just yesterday. Covered a lot. And so let's think about the case when this is just a point. So remember, in this case, that just means this is a complete fan. And when is it projective? Remember, there are some equivalences. This is projective if and only if there exists an ample torus invariant divisor. And then how do you check that? And there's several ways. And so the crucial thing is that there exists a torus invariant divisor D such that its support function and what property of phi D do you need to make D ample? So there's two words here. Yeah, strictly convex. Because remember, if I just had convex, what would I be? That'd be base point free. And then to make it actually ample, I need strictly convex. So the idea is we want to generalize this notion. And part of it is the idea is that we sort of want a relative version of this.
Excuse me.
Yep.
So for that last equivalence, right side only applies for ample for Cartier devices.
Oh yeah. So sorry. There exists torus invariant Cartier. Yeah. So let me give you the theorem. And this will sort of harken back to the definition of projective morphism that I gave last night. So I've got the same setup I have there, so I'm making that hypothesis. And remember that being projective meant two things. I sort of had there was a local aspect. I had an open covering down here, where up here it looked like just sort of a map into a projective space. But then those maps into projective space were mediated by a global object that was a sort of divisor down there. And actually, I take it back. So there was a global object here that all these local embeddings came from sort of sections of an object here. And so there exists a torus invariant Cartier divisor D. So that's the global object. And then it has to give the right behavior locally. And of course, in this case, locally mean on the affine open subsets here. So the idea is that, because notice in this situation, I have a torus invariant Cartier divisor. So I certainly have a support function. It's defined on the support, but it's not going to be strictly convex on the entire support, but it's going to be convex on sort of pieces of the support. And what we have is this is strictly convex on the inverse images of the individual cones. And so that's the theorem, and to actually so to say a little more about this, notice that notice that this says that notice that this right here is a convex set, and that's because this guy is convex. If you're going to define something to be strictly convex, you need the domain to be a convex set. And here's the kind of thing that could happen. So this is downstairs. Here's sigma prime. Suppose sigma prime just consists of, say, these two rays. So notice that the support is then these two rays. The support is not convex. And then suppose that upstairs I had something that so sigma's upstairs. So here's the origin. Downstairs, there's the origin upstairs. And suppose I had something that, maybe it was, so here, I might have a ray going out, and so sigma might look like this. So in a sense, it really does look like just, so sigma just looks like two sheets of paper that sort of meet along an angle. And so notice that sigma, so notice that in this case, that in this case is not convex. So it's meaningless to talk about this being convex here, because, if I were trying to define convex there, I'd have to, compare values here and here and on this line connecting them. And so that's the point, is this is the best place we have. So that's really the best kind of result that you can hope for in this. What? So, oh, there should be a bar there, yeah. That's right, because that's the same bar there. So let's see, so what else do I want to say about this? And so the idea is that, you see, once I get here, I get a lot of results about this. And so when I get strong convexity here, this is where you actually get a good notion of what's going on. And so basically, when you look at this part of the fan, so in a sense, when you look at phi inverse of U sigma prime, so see, when I look at that part of the fan, mapping down to here. So I mean, like, if this was sigma prime, if you're looking at this part of it, then see, that's in pretty good shape, and there the strong convexity, and there you really would get, using some sections of this guy, you would get a map into projective space. And so the idea is that, so this strong convexity guarantees that you get, locally it looks like something projective. And then this is, remember that there is also the global thing, and that's what this Cartier divisor does. That's the line bundle that I called capital L last night that sort of glues everything together. Then I want to say one more step that's sort of part of this, that also relates nicely to what we were doing here. So the point is that right now that and that look like they're sort of disjoint from each other. So let me give one more result that sort of makes things fit together. Because notice right here, the fact that I've got stuff set up, this map is guaranteed proper. And then the question is, what makes it projective? And the answer is, the strong convexity. And so let's look at, in order to prove this theorem, we have to look at that situation. And so a key step in the proof, and this will be where I end, is theorem 7.2.4. And I need something toric and proper. And so notice that that's what I have here. That's also what I have here. So there are three things that are equivalent. X sigma is quasi-projective. Phi is projective. Now notice that that's, the fact that this guy is quasi-projective and that guy is projective, that's part of that theorem. So that's pretty nice. In fact, those two, in this context, those are actually equivalent. And then there exists a torus invariant Cartier D such that the support function is strictly convex. And then there's one more part that's not in the book, but that I can add. Because of course, if I have a divisor, what geometric object do I get out of a divisor? Is it a polytope? Polyhedron. So remember that a divisor, a torus invariant divisor, gives us this PD. And so this is a polyhedron. This is a lattice polyhedron. Where this guy is, so I take the divisor, I take the polyhedron, I take the normal fan, I get a toric variety. And so this guy is exactly one of these. So the pictures fit together in a very nice way. And so what's going on is, here's the very general theorem. And this is one way of thinking about what's happening sort of over a local piece. And here's just a slightly different way to think about what's happening over the local piece. So I have two final comments I want to make. So I'm going to take my 5 minutes. So the first comment is that projective morphisms are important in the resolution of singularities. And so, for example, if you take any toric variety, dreadful, crazy dreadful, then there exists a refinement such that the induced map, so you have this induced map coming from the refinement, and that's smooth. So you have resolution of singularities. And you can do this in the toric context. And but the question suppose that I started with a projective variety. Now, that has a lot of singularities. Well, then you do all sorts of refinement to try to get something smooth. But we've seen in the examples Hal did that you can do some pretty weird things when you refine. It's actually easy to do various refinements and get something non-projective out of it. So the question is, can we assume X sigma prime is also projective? And the answer and this is some of the hard work that we do in chapter 11 of the book. So again, now this is now an arbitrary toric variety. Might not be projective or anything, but we still want this to be smooth. And the point is, you can always make the resolution map a projective morphism. And so by proving that you can do toric resolution of singularities using projective morphisms, that immediately implies that if this guy is projective, well, then that's a projective morphism. And what do we know about the composition of projective morphisms? It's projective, so that says, boom, that guy's also projective. So part of the reason that we wanted to do projective morphisms carefully here is because you really want them, you want to be able to do your resolution of singularities projectively. And then the other comment is just I want to say a word about section 7.3. Because this is a different idea about what a projective morphism is. Because if you take a vector bundle of rank R, it's a bunch of R-dimensional projective spaces. And of course, a vector space, by removing the origin and modding out, you get a projective space of one lower dimension. And you can do that globally. So you get, so this is a vector bundle. Here you get, so basically the fiber is isomorphic to C to the R. And here, instead of a family of vector spaces, you now get a family, and they basically all look like, this is a projective bundle. And they basically, the fibers are a projective space of one lower dimension. And what's nice is that in certain cases, if this comes as a direct sum, for example, of line bundles of torus invariant divisors, you can actually give this space the structure of a toric variety. That means that becomes a toric variety. That means you get something very nice here. So you actually get some very pretty examples of toric morphisms from vector bundles. So sorry to keep you late, and we will resume at 11.